All right. So I am Amanda Miller, the Associate Director of the National Consortium for Data Science, a project of the Renaissance Computing Institute, or RENCI, at UNC Chapel Hill, and it's my pleasure to welcome you to DataBytes. Just a couple of quick housekeeping items before our formal introduction of our speaker today. We ask that you add questions using the Zoom Q&A feature at the bottom of the screen. We do plan to leave about 15 minutes at the end of the presentation for a live Q&A session with our speaker. So speaking of our speaker, it won't surprise you to hear that some of the most exciting data science research happening right now isn't confined to a lab. It's showing up on our wrists, in our homes, and in the everyday devices we carry. With that in mind, it's my pleasure to introduce you to Jingping Nie, an associate professor at the UNC School of Data and Information Science, with an adjunct appointment in biomedical engineering in the UNC School of Medicine. And Dr. Nie is also core faculty with the Carolina Health Informatics program. She also directs the NICE-X Lab at UNC, which is the UNC Networked Intelligence and Cyber Embedded Systems Lab, where she and her team design next generation of wearable and AIoT platforms, novel sensors built from computational fabrics and soft electronics, paired with the machine learning and foundation models needed to make sense of what they capture. Today, Jingping will walk us through that full pipeline from wearable to hardware, to biosignal and emotion and analytics, to an intriguing idea that the smart speakers and devices already sitting in our homes could be repurposed to screen daily functioning, monitor mental health, and even help deliver AI-enabled psychotherapeutic care alongside licensed clinicians. And this is the kind of work that NCDS is thrilled to spotlight in our DataBytes series, data science with a direct line to human well-being. So, with all this in mind, please join me in welcoming Jingping Nie.
Thank you, Amanda, for a nice introduction. And thank you everyone for being here to this webinar. And it's my honor to share my work on from body signals to smart environments, embedded AI and sensing for wellness and health. So, despite the global efforts to improve healthcare, there remains a shortage of medical professionals. This color-coded map you can see over here illustrates the distribution of medical doctors per 1,000 people worldwide. While some countries have a relatively higher doctor to population ratio, I would say the overall numbers you can see over here are still not optimal. In addition, there are significant disparities between regions, which also highlights the ongoing challenges in ensuring equitable access to healthcare services globally. And this bar plot shows the number of mental health workers per 100,000 people, which means that the global shortage of mental health workers is even more severe. In some regions, getting to healthcare take a long time. Sometimes you can see like over a day. So overall, like we can see, healthcare today still faces major challenges. Too many patients, too few doctors, geographical barriers, infrastructure gaps, and cost constraints. To ease the burden on healthcare infrastructure and medical professionals, one key approach these days is shifting from reactive healthcare to proactive care. And with the growing demand, as we can see from this plot, the preventative healthcare technology services market is expanding rapidly. And surveys has shown that the number of IoT connected devices grows rapidly recently as well. These devices, as Amanda mentioned, right, including everyday wearables, home devices people may already have, and also like some public infrastructures, play important roles in people's everyday life and improve the quality of life from like different form factors. And with the effort of researchers and companies, as well as recent advances in artificial intelligence, we are moving from Internet of Things to artificial intelligence of things. So besides basic sensing, displaying, and reporting, researchers, right, like some of us, are actively looking into how to do modeling, predictions, and interactions to make the wearables and AIoT systems smarter. So this AIoT and everyday connected device open new opportunities for pervasive healthcare, allowing users to access support anytime, anywhere, either at home, in clinics, or on the go, through the ubiquitous monitoring, real-time data processing, providing remote and personalized healthcare, enabling proactive early disease detection, chronic condition management, and lifestyle adjustment, while ensuring accessibility and inclusivity. So, our research is dedicated to developing pervasive, preventative, and proactive mental and physical healthcare applications that benefit everyone from diverse socioeconomic backgrounds, not only the patients who already have access to professional healthcare. It also emphasizes continuous everyday monitoring and self-care, aiming to integrate healthcare management seamlessly into daily life. So, we're aiming to improve overall wellness of the public health by supporting fitness, mental health, and physical health. All my research projects are often driven by real applications and needs, where I first identify the needs in everyday life from different stakeholders, such as general users of all ages, fitness lovers, medical experts. And then, after communicating with them and understanding the gap between their needs and the current existing methods, I started to think, right, how we, like data scientists, I graduated from Columbia with electrical engineering, so like electrical engineers, biomedical engineers, and computer scientists who do work on digital health, preventative healthcare, and human-centered AI could contribute to bridge the gap, taking the advantages of the current advances in artificial intelligence and Internet of Things, making this different stakeholders' needs first machine readable and also machine actionable, and of course, enabling a wide domain of applications to realize their needs. So the core principle for my research to bridge the gap, including accessibility, pervasiveness, equity, effectiveness, efficiency, proactivity, affordability, and privacy awareness. And following these principles, I have developed wearable and AIoT systems using commercial off-the-shelf sensors, computational fabrics, emerging soft electronics, as well as advances of smart and connected devices every day to acquire biometrics and body signals, speech and conversations, as well as enable ambient intelligence. And with the backbone of my research project being embedded AI and sensing, my research focuses on three interconnected topics, my three little pillars over there, ranging from individual level to system level. Starting from smart wearables and platforms for emotions, fitness, and wellness, to model-driven biosignal analysis and emotion detection, and further scaling up to AI-enabled mental and physical healthcare in smart home environments. So to support applications requiring emotion recognition, I designed and prototyped low-cost wireless glasses based platform for continuous in situ biosignal acquisition and monitoring of users' facial expressions and real emotions. And real emotion including the dimensional emotions with balance and arousal levels and dominance levels. And then we also developed and deployed a soft fabric necklace for caregivers to monitor kangaroo mother care duration, the KMC durations, to track infants' heart and respiration rates through mixed electrocardiogram signals from both caregivers and infants. And this project was collaborated with pediatricians. And we're also developing contactless acoustic-based systems to accurately estimate running metrics using sound capture from a mobile device placed on treadmill. So I will dive in a little bit on this project because it's not only it's I'll say it's not the most fancy or exciting in hardware or engineering wise, but it's mostly correlated to my personal experience as a marathoner. So basically, there are about 50 million American participants in some form of running or jogging. And I'm a huge marathon lover and also a certified long distance running coach. I have interacted with hundreds or even thousands of runners during different events, some from running clubs or social conversational rounds. And the fun thing is that after they know me as a running coach and a PhD in electrical engineering and also a professor in data science, and I'm working on this machine learning, Internet of Things, and wearables. They love to ask me like, how could they improve their like running performance or like running without getting injury? And also give me feedbacks about the fitness tracking wearable devices they're using, like these digital ones. You know what? The fun thing I realized is that there are more runners than you thought who are really data driven. And the common running matrix runner usually use or like care about are cadence, ground contact time, and balance. Definitely, there are other like biomechanical related running matrix. Those are like people are discussing like every day and watching on their like watch faces to see, okay, what are the strategies to prevent injuries and improve their running performance or running efficiencies. And also, like as I mentioned, running metrics are like important to help preventative injury, monitor running performance, and improve running efficiency. And also note that, like although treadmills today have a lot of metrics, but they don't provide you running form related metrics, right? They usually provide you speed, distance, inclination, etc. So how do we like measure running metrics these days? The professional fitness labs usually using very advanced like motion capturing systems such as Vicon. Although it is accurate, but not everyday runners have access to it, and it costs like $100 per test. I mean, I don't want to spend like $100 every other month to do the test. And then like you become a sensing researchers also investigating alternative systems using flexible tactile wearable sensors or millimeter wave reader. These setups are still not fully portable and also still expensive, so that's not really handy to use in daily life. And now like in the market devices, right? Like wearable, like sport watches and running pods are popular for runners to track running metrics. These devices usually cost a few $100s. And there are smartphone apps that are using built-in sensors of smartphones to estimate running metrics while people wearing smartphones during running. But all these methods still contains rigid part, which would like irritate like user skin due to repetitive friction. And thinking about you may run more than 30,000 steps during a 3 to 5 hour like long run or marathon race. The skin irritation are not funny. And these commercial wearable devices are also not accurate, especially for indoor treadmill running. Then I realized, okay, there's a need for comfortable, accessible, accurate, and real-time monitoring of running metrics of like all treadmill for treadmill runners or indoor runners. And then one day, when I went to the gym at school, see, all of them bring their smartphones and place them on the display console over there. And also, like we noticed that when people running with different speed and different running format on treadmill, their feet will hit the treadmill belt with different angle and power, generating different treadmill running sound. The running sound captures a lot of information. The combination of the informative like acoustic signatures and the habits of treadmill runners suggesting an exciting opportunity. So can we directly use smartphone placing on the treadmill to extract the rich information from the treadmill running sound as estimated cadence, ground contact time, and balance? Smartphones already have the computing resources and sensors we need, right? So imagine this way, right? Like it's in everyday like settings. It would be wonderful to have such a system when you like running in the on a treadmill in any public gym. Maybe there are other folks like chatting or using other equipment next to you. You turn on your treadmill and start it to run. Your smartphone sits on the display console as usual, and your feet start to hit the treadmill bed. They generating unique running sounds based on your running forms and matrix. And now your smartphone can capture and analyze these sounds. And you can get also like real-time visualizations as well as real-time feedback. No extra devices or wearables are needed. However, realizing such a system presents several challenges. First, there was no publicly available treadmill running sounds dataset. We also need a generalizable and robust model that can estimate running metrics across diverse runners and noisy public gym environments. As such, we like to collect data in public gyms in real world. We observe that like commercial off-the-shelf wearable devices are not accurate, especially for indoor running. I will also show some like numerical comparison over there. So portable and reliable experiments design and ground truth collection methods are tricky. And we would like to implement our systems purely on resource-constrained mobile devices to be like privacy aware. So considering these challenges and needs, my electrical engineering knowledge and coaching experiences came together to design the experiments procedure for the data collection. So in our setup, we use like two smartphones, one on the treadmill running, one like put on the treadmill to collect the treadmill running sound, either horizontally or vertically. Another one is a video phone, placing right behind the treadmill to record the running video. And we use the computer vision based methods to generate the ground truth of running matrix based on the recording from the video phone. And we'll have subjects to wear one sports watch and a pair of running pods to be the ground truth or baselines to evaluate. And this like run scribe running pods is calibrated for each runner. And we recruited 61 valid subjects and having them to run at constant speeds from like 5 to 10 miles per hour for several minutes, yeah, depending on their proficiency in running. And subjects choose, how long they would like to run, right? And we will also give them like enough resting time before like different sessions. And in total, we collected like 363 running sessions, totaling 40 hours of data. And the data were collected from 24 treadmills in 13 different public gyms. We also sync the data from multiple devices to create a database to train and evaluate our approach. All right, now let me jump to the details about our like system, how our system works. The mobile device continuing capturing the treadmill running sound, and sliding windows are applied to enable real-time analysis. And for each windowed audio, mean variance normalization and denoising filtering are applied in the time domain audio signal to mitigate the discrepancies in the runners and the treadmills, as well as like the environmental noise. And then the frequency domain acoustic features are extracted. We test out different acoustic features like showing over here, and then acoustic features are passed into the machine learning model. And for our model, we also evaluate different like prediction methods, including like sequence to sequence, like more classification, regression, as well as different networks. Remember that we would like to run on resource constraints mobile platforms, so we don't want it to have like too large or too fancy models with high latency. So that's the reason like in my later work, I may like show more about, okay, more like foundation models, how we're leveraging that to take care of different like domain variations or like more like noisy scenarios. But in these particular applications, um, yeah, we are trying to sort of like just like keep it limited. Yeah, I saw like one questions in the Q&A sections. What's your thoughts on overcoming short of deploying bespoke medical sensing with specialized user agreements with usually adopt cost more in general? Oh, yeah. Thank you, Andrew, for the last question in the chat. So I think later on in my talk, I will talk more about, okay, when we're dealing with mental health, there are some like considerations over there. So I will answer all the questions together at the end. Thank you for the nice questions. Yeah, and then like for our whole setup, right, we're like different like mix and match and micro benchmarking with using like MFCC and male frequency spectral coefficients with root mean square energy of the spectrum with like regression methods using multi-layer perception model in a multitasking learning setup, right? Sounds like more like straightforward and also like it's very computational efficiencies actually performs really well to estimate the cadence and GCT per window and satisfying our design requirements. And after then we averaging the values for all the windows sliding through this timestamp, we get our final estimated GCT and cadence. And finally, we visualize the estimated results on the graphical interface of the mobile device. So actually, I have like a demo video showing over here what's happening. I'm not sure if the voice is properly shared, but we basically want to show that we have the suggested cadence and GCTs for each users, and a user can, set their target over there. And users can also choosing like different like modes. And for illustration purposes, we're showing the twin mode over here. And you can see the previous set target and real-time cadence and GCT on the smartphone. And also this runner is asked to intentionally adjust the cadence and GCT to show the real-time estimation performance. So you can see like when he increases cadence, our system like sort of can measure everything basically I would say with 1 second within 1 second's delay to getting like everything like purely running on the edge. All right. So more quantitative system evaluation. So I'm plotting like the precision error distributions for cadence estimation on the test set. The smaller the error, the better. So overall, our system could accurately estimate the cadence with mean absolute error of 2.9 steps per minute, and which significantly outperforms the performance of like most of sport watches, including like Apple, Garmin, and Coros. And while the $500 like running pod run scribe shows smaller error in cadence, but noticeably that like run scribe sometimes significantly overestimate the runner's cadence. And also remember that, right? Like run scribe was calibrated like to each runner, while our system does not need any like calibration phase. And also for ground contact time, note that sport watch usually do not provide this matrix for the treadmill running. So we only compare our system to the run squat running pods. We can also say it again. Yeah, our system actually outperformed run scribe with smaller errors in estimating GCT. And again, like run scribe loves to overestimating the GCT. All right. So this is like a straightforward, I also or example I want to show that using everyday devices, right, can actually helping us to enable a variety of new applications with already existing like hardware form factors over there. And also like making the system non-contact using mobile devices that treadmill runners may already have is a low cost and comfortable alternatives to the wearable devices. Um, and meanwhile, we are also like collaborating with researchers focusing on like programmable matter and metamaterials. We're developing a soft mechanoacoustic wearable devices-based system for monitoring vital signs and running metrics using deep learning. So, which will benefits for both indoor and outdoor running. And these like new steps, I think, can directly answer some like our new Q&A questions over there. Uh, so what happens like listen to something loud? So it's actually like so thinking about the reason like the nature of like the users placing the phone on the treadmill, right? So it's not only like the sound propagates through the ambient air, it's also propagates through like the physical let's say material of the treadmill per se. So it will like naturally um I would say the everyday habit will naturally sort of block out a lot of like these ambient noises. And also our new devices like using this mechanical acoustic like body sensing this kind of way. It's under developing, so I will not talk about too much, but it will like also naturally to it will only sound everything like have physical connection to this device. So like any ambient noises will not be a issue. And why not using sort of accelerometer and also like the purpose of calibrate. So we never like calibrate our device. So the calibrated shoes is like those are for the baseline comparison, right? We're showing okay, our setup do not need to have any calibration, but the commercial run scribe running pods does need it. And why do not using IMU based stuff? Because there will be you need to wear extra stuff, right? The purpose for this device, so for example, you can also wear your phone on your wrist, and a lot of running apps did that, but you still need to have something on body. And for this particular application, is how can we make it more comfortable so users do not need to wear anything because of their nature habit is to placing their phones on the treadmill. So yeah, hopefully this answers all the questions in the Q&A sections. All right. So beyond fitness, so we are also like developing like audio wearable platforms for construction worker safety that detects and localizing like different approaching vehicles. And all right, so I designed like this kind of like embedded AI and wearable platforms, and we also have like some other ongoing like soft fabric based wearable designing, collaborating with orthopedics in our lab, but due to time limit and also the preliminary stage of this work not published yet, so I will not show too much. But if folks like are interested, we can talk more like offline. Um, and so like we do like this kind of like different form factors design systems, right, and software algorithms over there. So we're also investigating different like more advanced computational methods not running on the edge to analyze different biosignals or body signals. So I began my work by exploring the differences in the neural representations corresponding to the different linguistic levels among bilingual individuals using electroencephalogram, EEG signals where I successfully decode the six-level second language proficiencies using neural representations with over 83% accuracy. And building on the experiences with EEG during my internship at Apple, we also developed frequency-aware mass autoencoders for multi-modal pre-training biosignals. And this approach makes like the trained model more robust in the real world application scenarios. And we're also carrying it like currently they're doing the sort of pre-training and domain alignment sort of like investigations in my lab in different setups. I will like explain more in details. So so why like using pre-training, right? So like the motivation is there's a lot of like publicly available data sets, maybe from same modalities, but they are coming from like different data collection devices or different subjects, especially I think for people who is doing like this kind of wearable devices or like doing, I would say doing some like image or like medical or fitness or health related like data collections, right? This is a like I would say common pain point over there because it's very hard considering the time and effort and money wise, right? Like it's very hard to scale it up to large scale data collection or like running into trials. And then like there are also like locally collected data in lab during like, prototyping thing, right? So how can we like help like leverage like the different like pre-training and then think about okay how could we better doing like inference and that adaptation over there to enable better customize for new applications is something like we're currently actively investigating on. So for like one example is like what we're doing is we're looking at the wrist, different like electrophysiological signals on the wrist and lower arm area, where like it contains wrist ECG signals, contains like anything about your heart and respiratory thing, as well as like because it's like on the arm, it will like combined and also in I would say like they will influence each other with like the EMG with the muscle signals over there. So what we're trying to do is, okay, we have a like very straightforward setup over there. We collect like both ECG and EMG signals together, and then we have the users to follow a stimulus with doing like different gestures, so we can have some okay. Well, while the user doing the gestures, how how bad will it influence the wrist ECG signals? Because like usually like in the literature, when people collecting ECG signals, users are at risk at rest. So steady state, not moving around in the like in the real day scenarios. Um, and then we're also doing like we after we collecting the ECG and the EMG signals at different like sampling rates, we then do different ways like okay, either we comparing like with digital signal processing based methods with like self-supervised learning like pre-training, and we are using like different pre-training methods. One is like transformer based like mask autoencoder, and another one is 2D CNN based mask autoencoder. The reason we are using like two different like pre-training methods is like the intrinsic, I would say, characteristics of the signal per se, while like ECG contains more temporal information, while like EMG has more like I would say frequency domain like informations over there. That's the reason we select one like is more focusing on the temporal time domain like signals like design the master autoencoder, and another one is like 2D based one. Yeah, so and then like we do like the okay for the downstream how we are evaluating the pre-training methods is we're doing like different like cardio parameter estimation for heart rate and heart rate variability as well as like different like gesture classifications, and we also compare it with like different like downstream tasks or downstream models over there with either like neural network based or like the SVM based or like sorry or traditional machine learning based. Um, yeah, and so like these are like the setup for our like sort of like the I would say model architecture for different like the transformer based like mask autoencoders as well as the sort of the 2D based sorry and also like the sorry yeah this is like the transformer based like mask autoencoder for the ECG pre-training as well as the model architecture for the ECG downstream task while we are inference information to do different like cardio estimation. And for the cardiac estimation results, I will skip some details due to the time limit today. But we want to show that overall, the self-supervised learning methods show like lower intersubject variability and like better like heart rate variability agreements, which can show that this using like this pre-training can actually improve the robustness while we are trying to inference it like in a more noisy and also like across intersubject like scenarios over there. And for the gesture estimation results, we also compare it with like DSP, digital signal processing related ones, as well as like the sort of the mask autoencoder ones. But for this particular case, as it's a preliminary study in the lab conducted by like our like undergrad and master students, we still like the methodology we are like looking for now is still like the DSP methods is still giving our slightly better results, and like we're still looking at okay why it happens, and that carries out to like the another like sort of ongoing work we're trying to do is we are also trying to see okay because we're also trying to see like different sort of pre-training methods over there, right? Using different encoders, like the TAP-MAE is like the ones we tried and like we just showed, and we're also trying like other like trying to adapt other like pre-training methods like biofilm, which like having like more frequency domain information over there, which is a frequency aware like mask autoencoding over there to see why it's over there and which one's better. And we also showed like different setups, right? How should we pre-train over there and to enable a better like downstream like results. Either like we'll transfer from okay, the same signal like chest signal to race signal or like other area like does that work, right? If like for example, if you want to just like pre-train from like signal from the same area, it maybe have limited data. But if you think about okay, ECG or EMG like all over the body, it may gives you more data to enrich your training sets, but it may also be like less relevant to like the target signals you are interested in, right? So also trying to say, okay, will this be helpful and how will the performance be different over there? So I will also skip some of the like details over here due to the speech limit, time limit. And then like during like my time at Apple, we're also investigating different like machine learning methods for heart rate estimation and heart murmur detection based on phonocardiograms from a PhysioNet dataset. And using a two-dimensional convolutional neural network-based multitask learning methods, we achieve a heart rate estimation with a mean absolute error like less than 1.4 beats per minute and a murmur detection accuracy over 95%. Um, yeah, so I'll see like for the questions in the chat, do do you have any clean methods to go from R intervals to N? Sorry, I'm a little bit confused. What do you mean by N? Yeah, I will get back to the Q&A sections later. Uh, Yeah, so we're also like investigating like the different like salient representations of speech foundation models when we use speech for emotion detection. So the motivation is that like pre-trained speech foundation models, embeddings, right? Especially, for example, such as those like from like Hubert, have very large dimensionality. So can we reduce the representation size? That's a case-like representation of n-dimensional Hilbert embeddings for a speech utterance y being represented by like a vector hky and have the mean effects level to be labeled for each emotion dimensions, including the valence, activation, and dominance for y to be ly. And we define this cross-correlation based saliency, so we call it CCS, for each dimension of the embedding representations. And the gamma key here is the sum of the weighted cross-correlation between case dimensions and all other dimensions. And in our experiments, we have used the mean CCS to select the salient dimensions in pre-trained representations. Compared to our original like speech emotion model, after fitting in the speech utterance, we add salient feature selection modules after extracting the embeddings from Huber models. And we use the podcast dataset to evaluate our model. As we can see from this table, when we use 40% most salient representation dimensions, we can reduce the model size by around like 50% while causing minimum regressions in the model performance. So what we can tell from here is, okay, by trimming down the size of foundation models, by only looking at the most salient connections in the network, right, we can make it easier we can like shrink down the model, right? And also make it easier to advance like emotion recognitions into everyday IoT systems. All right, so right now I have like some experience in doing like more like hard sound and speech from like public available data sets, which are measured when people are at rest, right? Remember, I also did the running project. I also collect speech, breathing, sound, and phonocardiogram after we collected running-related data. These audio recordings are different than the public available ones. In particular, after having the participants to run at different speeds, they reach different exertion levels, and immediately after they stop running, we measure their phonocardiograms, heart sound, and using like this digital stethoscope. Here are examples of heart sound recording after one subject completed a lightly intensity and a maximum intensity session. And we can see the increase in the heart rate, heart sound amplitude, as well as like contains like exercise-induced murmur. Note that this is different than the pathological murmur I tried to classify in the previous project. And right after collecting the PCG, we asked the subject to read a short paragraph, took several deep breaths, and say something spontaneously. And here is an example when a subject reading the same paragraph after she reached two exertion level. We can see that subject's heart sound is still recovering, right, at this moment after this high intensity run. You can see it's like this is decreasing over there. And also this like sort of like high intensity has more breathing breaks taken to read this paragraph. Again, like those like our exercise-induced crackles and whistles, so not pathological. So our preliminary results show that we can use these body signals to decode the exertion level. For spontaneous speech and reading paragraph snippets, we can achieve an accuracy of 80, 86% using male frequency spectral bands and the force embeddings layers of the pre-trained wave-to-vec based models as the features. And then if we're using the spontaneous speech, the accuracy can goes up to around like 90%. And then also, as I mentioned earlier, right, the speech after exercise will have different like breathing breaks. So there will be like somatic plus breathing pauses, or there will be like purely somatic pauses because I need to stop for a somatic reason. And maybe there are only like breathing pauses. It should not happen, but like the runners are short of breath because of the elevated exertion level. So we have like different like annotators to do frame-wise annotations, and also we're using the chest belt respiration as a gold reference. And we got the data set, but unfortunately, like because like we're collecting it like in the real world scenarios, right? So the data like sort of distributions are severely imbalanced. Sorry, I also see another like questions in the Q&A sections as a hand gestures a method to fine-tune the macro facial expression eventually. This hand gestures is a I was different project than the sort of the glasses based one to collect any like this like biosignals on face. It's theoretically those are like maybe correlated if you are like at specific events, but I would not say like hand gestures is like it's not used to fine tune like any facial like micro facial expressions over there to answer the questions in the Q&A. All right, so due to the time limit, I also try to skip some of those. So basically, like we also try out like different like features and also like different like downstream like model setups and also like using like okay purely acoustic features were combined with pre-trained like this acoustic foundation models features and also using like either do it using one stage directly end to end or have two stages to detect where the pulse is and then do the classifications later on. And overall, we can see like the results for the somatic breath because we are using like these pre-trained acoustic speech foundation models, we can achieve accuracy of like around 89%. But for the breathing only and breathing plus somatic, especially for breathing only, the performance is not that good because first of all, we have like, I would say like not a lot data from the data we collected. And also like the breathing sound per se is very subtle and the actual cases during like the experiment data collection is like more rare over there. So this is also like why we're trying to move forward in our later studies. And also something else related to like this post exertion thing is we talk about the heart sound, right? So, so as I shown like on the left, there will be like different like exercise-induced like murmur or pathological murmur, or no murmur, like because of okay, after exercise, there will be exercise-induced murmur, but like the previous data sets, like public available ones, right, have pathological murmur. So we're trying to curate a data set with all of those in collaboration with cardiologists here at UNC. So we collaborated with like the cardiologist, and we come up with like the I would say the ground truth labels for those. And we also want to show that. So for basically on the bottom left is showing the data distributions of okay how many data we have for murmur and no murmur, like also like how many we have like for like this pathological murmur over there, and what's the sort of how we're doing this train validation and test by splits over there. And we also tried like on the top right, we're trying to show like the confusion matrix with like the publicly available models. We want to show that it's not doing well for differentiating like the exercise-induced murmur and pathological based murmur. And after we fine tune and also we adapt like different steps like to like the our methodology, we can with the like cardiologist label data, we can increase the accuracy of detecting okay differentiating pathological murmur and exercise-induced murmur and achieve a more robust accuracy over there. So we can show, we can see from this plots like with like the acoustic feature we selected, and like we can finally achieve like a overall accuracy around 91% over there. All right. Now I'm going to switch topic a little bit to talk about my research at the system level and also like particularly in the smart home environments. Um, And so in the fields of like human-centered AI, ubiquitous computing and mobile computing, right? When talking about mental health related research, the key research matrix may include emotion states, vital signs and biomarkers, human activity recognitions, social interactions, and other interactions and interventions. Um, the This matrix typically rely on inputs such as biometrics, ambient intelligence, as well as speech and conversation. And for example, the researchers have investigated using radio frequencies to detect four emotion states and 10 classes of human activities such as walking, stretching, and waving, etc. And researchers also explore like using heartbeat modulated ultrasound echoes in the ear canals from active noise cancellation headphones actually, to detect heart rate and heart rate variability. And researchers also using channel state information from Wi-Fi to monitor human dynamics. A conversational web app was proposed to support dialectical behavioral therapies, which only focus on psychotherapeutic practices and can handle only closed-loop response. As you can feel, only a few researchers in our fields finally connect this matrix to mental health screening and provide psychotherapies to support mental wellness. So how do like mental health experts assess like mental wellness? Traditionally, they use screening tools such as like mental status examination, adult ADHD self-report scale, PHQ-9 for depression assessment, GAD-7 for anxiety disorder. And this screening usually conducted by licensed professionals, which has a barrier for patients with like low income or like remote area. And collaborating with psychiatrists, we actually designed the AI-based like sort of like online mental status examination over there. But like due to the time limit, I will also try to escape for the like last part. So then like back in 2020, like we had the chance to talk to psychotherapists during like some events. Like they were like in the largest like mental health counseling institutions in the New York City areas during a PhD over there. And I said, hey, we're also doing like these mental health related topics, right? And introduce the mental health related research in our domain and how we automated like the sort of mental status examination process. She said that's cool and helpful for them. But she also mentioned to me that during their clinical practices with patients, they also care a lot about the dimensions that cannot be directly reflected by these questionnaires and exams and transformed from this matrix. They chat, right? For example, instead of ask a pop-up survey asking on a scale of 1 to 10, how's your mood today? They might ask like more open-ended questions, like how. sort of like how's your relationship with your family members, and are you able to like make decisions yourself? So how does like a psychotherapy piece like visit usually looks like? Um, they usually sort of starting with okay, chatting with your daily lives, and then trying to map that to their clinical matrix, including like day-to-day functioning and also like different like DLA 20 like or like DSM-5 standard, and then they will um, do like sort of provide personalized and targeted evidence-based treatments like motivational interviewing and cognitive behavioral therapy, CBT, right, to provide these psychotherapies. Um, so like I would say like and so what we do is like okay after like talk to the therapist and understanding the gap over there, we came up with 37 dimensions to screen day-to-day functioning to infer like mental health status. And we also define like three scores for each dimension, zero for doing well, one for some issues but not urgent, and two for the cases that need more attention from healthcare providers. We also define rubrics to give these scores in each dimensions. And there are also like different like design requirements over there, right? We want like minimum like lifestyle disruptions, and also we want privacy awareness and also accessibility. So to bring some of our vision to practice, we built up this Kitty collaborating with licensed therapist. And Kitty is the first seamlessly connecting home AI therapist, consists of four modules to screen the comprehensive day-to-day functioning of the occupant and provide appropriate psychotherapeutic intervention and empathic validations depending on the physical and mental status of the occupant. And so we also like implemented like proof of concept prototype of Katie conducted studies over like 14 days and 24 weeks, which includes like in-lab and at-home sessions. And therapists also provide bi-weekly check-in during the 24-week study. So I will sort of skip like the details of like what our how our system eventually going, but I want to mention like we just like doing like during like converse with like the user in a natural way, and then we will after we doing like this like response analyzing, we understand where the how well is the user in that current state. We'll provide different like psychotherapeutic intervention, and the motivational intervention will go through like reflecting a clinical procedure called like reflection validation, and we also incorporate like reasoner validator and guide powered by large language models to enable like different like quality check, and also like to validate if the user response is valid and also within the current like scope. And otherwise we were trying to get the user to okay still like following conversation flow, because the users may have like cognitive distortion. And then like also if like the user provides the follow-up response, then we will like validate provide like empathic validations over there to validate the users to provide suggestions. And overall, like the accuracy is like we having like the psychotherapist like we collaborated to provide us data sets and also like label the results out of like our like real world implementations and achieve a very promising accuracy. And then at the end of each conversational sessions, we also have like the cognitive behavioral therapy. Again, we have like questionnaire, reasoner, and guide to ensure like the like validity and like sort of utility of like the whole process over there. Like overall accuracy is still good. And we also like the sort of form factor we use to converse with the user is using like smart speakers and also smartphones. And we're also using ambient environmental sensings to detect like some activities over there. We want to, this is like the platform we designed. We want to make it seamlessly connected and also like being very friendly to lay personnel. So that's the reason I just like pass the slides. We show like the high school students, when we are using this to do like outreach events, they have no issues of using any of those. Yeah. So basically this ambient devices can also like detect like around like 94% of like the different like activities that we can sense in the at home. And then like for some like concerning like activities, we also like take advantages of like home robots to interact and to double check to check in with the users. Like to yeah we using like a sort of a vacuum machine form factor because most of the home have it, and using 2D lidar to like having it always on instead of like using like actually camera, because we want it to be privacy aware using more like low fidelity like sensors over there. And overall we can like sort of after we check in the user, we're using LiDAR to find the users. We can turn on the camera, and we all the like the cam within like the image capture from the camera. We also come up with like sort of a more like using foundation model based way to better differentiate, right? Like either this kind of like concerning behavior since from the ambient sensing, right? Like let's say the alcohol, right? If like people having like drinking at their dining table, it's basically benign, right? But if it's a hot liquor like lying on the floor, it's something like we need to bring up to a concern. So we're actually using like large language model plus like vision language models to differentiating like this particularly like subtle differences and to including like all like improving the accuracy of like the concerning events detection by I would say significant amount over there. So overall, like during our studies, we do like um, sort of like the collaborating like psychotherapists do like the Wilkinson single rank test for the 14-day study and found a statistically significant decrease in the concerning dimensions for the 20 subjects. And for the 24-week studies, therapists observed improvements in anxiety, depression, and also like functional different difficulties different ways. All right, to summarize, Katie provides comprehensive screening of the first effective psychotherapeutic interventions and is clinical validated. Now let's come to towards like the first questions I think in the Q&A sections about okay the privacy concerns and other like concerns over there. So yeah, in collaboration with like when while we're using these different like sensing mechanisms or like conversational or even intervention mechanisms, actually like medical scenarios, we collaborating with psychiatrists, psychotherapists, behavioral scientists, and also ethical experts from like different institutions shown over here. We did like user study and survey with like with them, and also like focus group studies with like people with lived experiences, and also doing like this was done like with like sort of patients with a chronic cardiovascular disease, but with mental health issues. So we're asking them, right, like how do what are the questions or like what are the concerns for now, and also how willing are they want to use this different like AI techniques or sensing techniques over there, and how could we enable best like better robustness? There's a trade-off there over there, right? Better robustness versus the security, right? The limited, when we think about security, there may be like limited resources can be used where you need to degrade some like functioning performance, right? To ensure the security. So how can we make better design choices over there? So yeah, so basically like what they told us, okay, they're happy to using this AI related stuff, and also but they're concerning, okay, like they're leaking any like personal information to sort of like let's say proprietary models like ChatGPT or like talking to cloud, right? So what we do over here is like, for example, like one of our effort is trying to make everything on device, as you can see from our previous studies to enable embedded intelligence where users own all the data. So this also applies to our conversational models. We're using like, for example, for the conversational AI therapists, we're using like the small language models, and also we're using like on-device automatic speech recognition, and with like quantization and pruning to improve the accuracy and performance, and also like students did like different like benchmarking over there to improve the accuracy. Um, so let me quickly summarize what we have done. So basically, like sort of like we have like three sort of like the pillars spanning through like individual levels to system levels. And like currently, like in our lab, like what we are also doing is like different like multimodal intelligence, wearable network for in situ body sensing, as well as AI for wellness and care in sustainable smart home and indoor environments, as well as like the sort of clinical settings, other like yeah, for everyday pervasively indoor as well as like in clinical settings over there. Um, yeah, and before like I jump to the more questions, for like give a big thanks to like our like students working in like in my lab, and we like without them we cannot like making like huge progress, to making things forward. Yep. All right. Thank you. And let me jump to the new questions in the chat. What is I was wondering what about the stigma of office monitoring devices in public, i.e., large glasses and wrist monitors. Yeah, so to make sure I understand it right, so you are thinking about more on the sort of HCI, human computer interaction side, right? What will the how will the public infrastructure affect the affect the sort of the performance or the acceptance of the device, if I understand correctly, like large glasses and wrist monitors. Yeah, I mean this is kind of yeah a little bit confusing. But if I'm thinking about if you're thinking about okay, are we like or are you thinking about, okay, what is a form factor that's acceptable by the like users to use in the public form factor? Okay, let me answer in both, right? For example, if you are thinking about, okay, where like people now like I think more and more people using like Oculus and also like Vision Pros, right? But you may not see that much like wearing them on the everyday settings, but you can see like the Meta ribbon glasses, right? Like having now have like more popularities because of okay, people now are more adaptable. I think it's like it's not only like sort of technical challenges, right? Like okay, how can we make enable it to be in this form factor, but also like societal compacts over there, right? Like what is a widely acceptable format over there, right? Like let's see, right? You can see like let's say 10 years ago when like Google first came up with like this sort of the glasses, right? With like this sort of the first smart glasses with a outside like facing camera. People do not buy this idea because they say okay, privacy aware, blah blah blah. But now while people like starting to getting more and more acceptable to okay this digital device, you can see when like the Apple Watch coming out, and then like more and more people using sports watch, smartwatches these days, right? And also like different like other monitors like also like Aura Ring, right? Or like even yes, I mentioned like ribbon glasses. I think it's like more with it's evolving with the society. It's like okay, how like more and more people starting to feel the benefit of it, start to wear it, then they will not be judged by their peers, and then will sort of started to use it, right? Like for this, for example, for like large glasses or like wrist worn monitors, I think now it's getting more popularity. And also like for example, what we are also trying to do, right, is like embedding that into everyday like wearable or like everyday garment form factor. Let's say if you want to wear like the sportswear, like compression shorts, or like you want to using like this sort of like headbands, right? Like the sweatbands over there. People are using it for exercise already, right? So that's one like incentives. Like that's a very great question. One incentive is like why we design something in this form factor because people already start to use some of it. They are already in their habit. Then there will be adherence to using this device and will be more and more widely acceptable and make real impacts. Hopefully that I answer the questions over here.
Yeah, I think you've done a great job actually moving through some of these questions. Thank you so much, Dr. Nee. It's been really just an absolute pleasure to hear all of the information you've been able to get through today. And hopefully, this has been inspiring for folks who have attended, and maybe some folks will be reaching out. Who knows? But thank you again for your presentation today. We do have just a few closing slides I want to share before we wrap up. As we mentioned, Dr. Nee is part of the School of Data and Information Sciences at UNC, and they are hosting, I believe it's the fourth Data Science Day on Thursday, September 24th. Applications are currently open to submit short talks and poster abstracts for all students, faculty, and staff at North Carolina-based institutions, so UNC system-based institutions. And folks would love to, we would love to have you participate. I will be at the event hosting a table for Renaissance Computing Institute with one of my colleagues, and it would be a pleasure to see some of you all there. If we could just hop on to the next slide, I am thrilled to tell you about our next DataBytes event in October. DataBytes events happen every 2 months, and the next event features Dr. Adam Kiefer from Exercise and Sports Science here at UNC. He has been developing a really cool tool with our friends at Amazon Web Services called Grow, which is the Grant Research Opportunity Wizard. So it's a really exciting tool he'll be sharing about at our next DataBytes event. And that is it for today, everyone. It would be an honor for you to complete our closing survey so we can learn how to improve future events. We really do look at those and provide feedback to our speakers when it's relevant. But we're just delighted you've shown up today and taken the time to participate and li actively listen and provide all these great questions for Dr. Nee. Dr. Nee, thank you so much. It's been exciting to have you here, and we look forward to future exchanges between you and NCDS and Renzi. So thanks so much, everyone, and we will see you soon. Take care. Have a great semester, all. Bye-bye.